Let's now look at our final topic in series, and that is how to handle the error when a series doesn't alternate. And when a series does not alternate, its first omitted term does not capture all the error. And that's because when a series doesn't alternate, you're always adding terms, adding positive terms. So you're getting closer and closer to some elusive value, but you're never quite reaching it. But even though that's happening, it is possible to adjust the first omitted term so that it does capture all the error. And that technique is known as getting the LaGrange error. LaGrange was a French mathematician who did a lot of great work in calculus, and he's credited not only with developing this technique, but also proving why it works. So what I have written down below here is Taylor's theorem. For any function, you can build a series centered at any location to approximate that function. And I've written out the first n terms of Taylor's series, and if you stop after the nth degree, what you've created is the nth degree partial sum. So if you stop after the third degree, it's the third degree partial sum. If you stop after the fourth degree, it's the fourth degree partial sum, etc. The first term you omit is the n plus first term, and there it is. If I had placed here a, so if I had evaluated the n plus first derivative at a, where the series is centered, I would have gotten precisely the first omitted term. But we're going to choose a new location to evaluate the n plus first derivative that will make this part larger, which by extension makes the entire first omitted term larger. And by inflating it, we will make it large enough so that it captures all the error of all the subsequent terms added up. And this exploration sort of shows you how that happens. There's a fair amount of detail in this exploration, but what I want to do here in this video is just give you a little more holistic view, so I won't be providing quite as much detail as if you were to work this as an exploration. All right, so the function I want to work with today to demonstrate all this is the natural log of 1 over 1 minus x. And I picked that function because it has a very nice Taylor series expansion. It's centered at 0, so you could call this a Maclaurin series as well. But there is the series out to the 5th degree, and it goes on forever. And what I did is I placed in y1 the function itself, and then I placed into y2 the 4th degree partial sum. So I just stopped right here. And I've provided graphs over here on the right of both of those expressions. The blue curve is the actual function, and then the red curve is the 4th degree partial sum. And you'll notice that between -1 and 1, the two curves seem to be very close together. They seem to be converging. And if you zoom in on any location, though, you'll see that there is some error. So the function and its 4th degree partial sum are not perfect matches. And they are at x equals 0, but as you move away, that error becomes more pronounced. And you could reduce that error, though, by adding more and more terms. And what I want to do in step 4 is show by using the ratio test that the interval of convergence is indeed between -1 and 1. So I'm going to go ahead and do that. If you express this series using sigma notation, it would be 1 over n, x to the n, with n starting at 1 and going on forever. And that means the nth term is x to the n over n, just written a little more compactly. And then the next term, the n plus first term, is just x to the n plus 1 over n plus 1. And what I'm going to do now is apply the ratio test. So I'm going to sandwich between -1 and 1 this limit, as n approaches infinity, of the n plus first term divided by the nth term. And rather than divide by that, I'm going to multiply by the reciprocal. So there it is, sandwiched between -1 and 1. I notice that x to the n plus 1 over x to the n simplifies to just x. I can remove it from the limit expression because it doesn't depend on n. And then I'm left with n over n plus 1 inside the limit. And that limit, as n approaches infinity of n over n plus 1, is equal to 1. So that means my interval just goes from -1 to 1. That's my interval of convergence. And it's an open interval because I haven't yet evaluated the endpoints. But let's do the endpoints as well. Let's evaluate them. So at x equals -1, the left endpoint, if you put -1 in for x, you get this series. It's a harmonic series that alternates, and that converges because 1 over n is approaching 0 and the series alternates. At x equals positive 1, the other endpoint, the right endpoint, when you put that in for x, 1 in for x there, you get, again, the harmonic series, but it doesn't alternate. You get 1 to the n, which is always 1, and that does not converge. So we can refine our interval by adding an equality to the left endpoint, and there is our interval of convergence. And what that means is that we can use this series to model that natural log function up here as long as we use x values in this interval. And what I want to do is use x equals 1/3 to demonstrate the error and then how to capture it in the first omitted term. So what I have done on my calculator, I have these functions in y1 and y2. y1 is the function, y2 is the fourth degree partial sum. If you evaluate them each at 1/3 and then get their difference and take the absolute value, you end up with a result for the error of 0.001144, and it keeps on going. So a small amount of error, but it is there. And then if you evaluate the first omitted term, and the first term you didn't use was 1/5, 1/3 to the fifth. If you evaluate that, you get a decimal point, and you get 3 zeros, and then it continues 8, 2, 3, etc., etc. And you can see that the first omitted term does not capture all the error. It's too small. And that's what we expected because this series doesn't alternate. So what we're going to do now is we're going to take that first omitted term and make it large enough to exceed the error. And here's how we do that. So this is called the LaGrange error. And here's how it works. So here is the structure of our first omitted term. It's 1 over 5 factorial, the fifth derivative evaluated at 0 times x to the fifth. And that, by the way, that fifth derivative evaluated at 0 turns out to be 4 factorial. And 4 factorial over 5 factorial gives you 1/5 x to the fifth, that first omitted term. But what we're going to do now is we're going to take that expression and we're going to change where we evaluate this fifth derivative. And we're going to look for the largest value, the largest value of that in the interval 0 to 1/3. Now, why that interval? Well, the series is centered at 0, and we're evaluating this function at 1/3. So we're going to look in that interval and find where the fifth derivative is as large as possible. So here is the fifth derivative as an expression. That's just the result of taking the derivative of the ln function 5 times. And I've graphed it between 0 and 1/3. And when you graph it, you find that this thing grows quite dramatically. So I had to create a y window that was pretty high. And you can see that it's an increasing function in this interval. So its largest value is way over here at 182.5. So we're going to replace this old expression of 4 factorial, or the fifth derivative evaluated at 0, with 182.5. And that's what I've done down here. I have 1 over 5 factorial. I have 182.5 standing in now for what it was before. And then I have 1/3 to the fifth. And that result is 1 over 160. And that is greater than that error that we had from before. That was the error that we saw before when we were looking at the first omitted term. So there is the error. And we've now created, in the first omitted term, a larger error than that. So now we've captured all the error in the first omitted term. And that's pretty powerful stuff. So LaGrange says, even though the first omitted term doesn't capture all the error, you can make it do so. And in this summary, I have shown you what that expression is that we evaluated for the fourth degree partial sum. Here is the first omitted term, and then there is the Lagrange piece of this term. And then if you generalize for the nth degree, it would look like this. So I replaced 4 with n. And then if you generalize for any function, it would look like this. So now we're not working just with the natural log function, but any function. The Lagrange error is 1 over n plus 1 factorial, the n plus first derivative, evaluated at some other location between where you're centering the series and where you're evaluating the series. And then there's your final piece of that first omitted term, x minus a to the n plus first. And the last thing I want to show you is how to determine how many terms you need to achieve desired accuracy. So we're going to again look at that natural log function, and what I'm going to do is take that nth degree partial sum, so this 1 over n plus 1 factorial, n factorial over 1 minus 1/3 to the n plus 1 times 1/3 to the n plus 1. That's the first omitted term in general for an nth degree partial sum, and I want it to be less than 1 times 10 to the negative 9th. So I want it to be less than this huge result, 2, 3, 4, 5, 6, 7. Less than 1 times 10 to the negative 8th. And to achieve that desired accuracy, what I did is I put this into y3 just so I could evaluate it, and I found that when n equals 25, I achieve this result, which means I have to use the 25th degree partial sum in order to achieve this level of accuracy. Now, when you're actually working on LaGrange error problems, like if you see it on the AP exam, usually they will provide you this number of 182.5 or whatever the number is. So they'll tell you what the maximum value is to place into that first omitted term. So all you'll have to do is write your, in that case, 1 over 5 factorial, put that value in that they provide, and then do x minus a to the 5th. And that will then give you the LaGrange error for the 4th degree. And that's it.